were you on break in the summer?
I don't know. I got summer school.
Lane? What camp did this pass?
All right. Yes, record. All right, so we're gonna just jump back in where we were. We left off talking about this alpha halo ketone effect. We talked about A values, and we talked about 1,3 diaxial interactions, so on and so forth. So today we're gonna start talking about another phenomenon with these cyclic systems, and there's a so when a cyclic system, a 6-member ring or something like that contains a heteroatom, then the dynamics change, the energetics change, and the preferences change for axial versus equatorial. So let's talk about that. Right, so before we talk about the anomeric effect, I want to show you another molecule, dioxane. Right, and you can see right away with dioxane, you still have your 3 axial sites. Then on the bottom face, right, you don't have that same axial interact 1,3 diaxial interaction because your lone pairs on oxygen. Right, they don't present a steric interaction. Right, so you can think about something like 1,3 dioxane, depending on where your substituent is. That's gonna really kind of dictate whether something is axial or equatorial based on the fact that, you know, those lone pairs on oxygen are not really, they don't cause any steric hindrance, right? So when you compare that to a just a regular chair with no heteroatoms, right? Again, you got all of these interactions here that can happen. We put a group down here. Right, you got 1,3 diaxial interactions on both faces, top and bottom. But with the something like dioxane, right, you can alleviate that with those oxygens being in the ring. And that's what we mean by a heteroatom, something that other than carbon, like oxygen, nitrogen, sulfur, something like that. All right, so let's talk about the anomeric effect. And this is related to 6-member rings that have heteroatoms in them. All right, and so I'm gonna show you, and this the concept of the anomeric effect is derived from what's observed with sugars, which the different isomers of sugars are called anomers, right? So if you have a sugar like glucose, and I'm just draw this out. So this is equatorial. This is also equatorial. This orange is equatorial. And then the OH here, let me change the color on that. This OH is axial. Right, so you can see everything is equatorial except for this one hydroxyl group right here, right? So this is the alpha version. And then in the beta version, never mind. All right, so this is the beta version where that OH is now equatorial. And the other hydroxyl next to it is also equatorial. All right, so this is alpha and this is the beta version. Right, but what's intriguing is that it's the alpha version that is favored with the hydroxyl axial, right? And that hydroxyl being axial and being favored, it's an electronic effect. Known as the anomeric effect. And again, most of your interactions are going to be either steric or electronic, right? So this is an electronic effect called what we call the anomeric effect. And when we look at it, what we can say is that in this case, the axial hydroxyl group is favored, probably similar to the same thing we saw with the alpha halo ketone effect, with the dipoles being opposite, right? Because if you look here, right, obviously this dipole is going in this direction, and then you have a dipole going in that direction, right? So the anomeric effect basically says, and this applies to alkoxy and halogen substituents on a ring that has an electron withdrawing group in it. So the anomeric effect in basic terms is if you have an electron withdrawing group in the ring, right? And you have in that electron withdrawing group, let me change that. If you have an electron withdrawing group as a substituent, and it's adjacent to an oxygen or some other heteroatom, then that electron withdrawing group that's the substituent that's adjacent to the oxygen is going to prefer the axial position. Right, it's going to prefer the axial position. And again, the reasoning is probably something similar to the alpha halo ketone effect, where you have the dipoles going opposite directions, decreasing the dipole, the polarity, and that in turn causes that axial position to be preferred. All right. And again, if that's the reasoning, then this effect is going to be stronger in non-polar solvents than it is in polar solvents. Right. So let's go take a step back. And if you look at a halo substituted pyran, right? Where we got a chlorine here. And then this is in equilibrium with obviously the ring flip isomer, right? Where the chlorine now is equatorial. Right? This is going to be your favorite isomer. Right? And there are a couple of reasons behind that. One reason is the fact that you have lone pairs on oxygen here. And you have that lone pair is able to donate into the sigma star orbital of the carbon chlorine bond. So that sigma star orbital is aligned with the lone pair on oxygen. Right, so that's a stabilizing interaction. Right, and if that chlorine wasn't axial, then you wouldn't see that. You wouldn't see that interaction between the lone pair on oxygen and the sigma star orbital in the carbon chlorine bond. You wouldn't see that. All right, any questions about that? So what you'll see in this particular case is a lengthening of that carbon chlorine bond, right? Because you're donating into sigma star, or you're overlapping with sigma star. I heard somebody unmute. Go ahead.
No, I was just going to answer you, Dr. Russell. That's all.
Okay. All right. All right. So that anomeric effect is again, you see it when you have a oxygen in your ring and you have an electron withdrawing group adjacent to it. And depending on what the other substituents are and what the electron withdrawing group is, that's going to determine like the type of interaction you see, right? You're not going to donate, even though oxygen in the pyranose ring up top is very electronegative, right? You're not going to donate into the CO sigma star, probably because it's too high in energy. But the oxygen is going to have a huge dipole, right? And then if you compare that to chlorine, chlorine is a much larger atom, so that bond is a little bit longer already. And so that sigma star in the carbon chlorine bond is a little bit more accessible. All right. So with that being said, when you look at the effect of having heteroatoms in the ring and how it affects the reactivity, how the actual conformations of rings can affect the reactivity. Let me show you one example of that. And then we're going to talk a little bit about A12 interactions. We already talked about the A13. We're going to talk about the A12 interactions. And we can go back. I didn't pull up the problem set, but I know there was one more problem on there that dealt with A values and figuring out what the most stable conformation was for a chair that had a bunch of substituents on it. So we'll go back and look at that. All right, so let's talk about this acylation reaction of cyclohexanol, and we want to talk about the It's 4-tert butyl cyclohexanol. So let me put that in here. All right, so my tert butyl is obviously equatorial. That's a huge group, and it does not. It costs a whole lot of energy for that to be axial, like 22 kilojoules per mole for that to be axial, right? And if we compare it to this isomer, and the question is which one is going to react faster, all right, in an acylation reaction. So you treat both of them with acetic anhydride, and you end up with the acylated version of this. I'm just going to write out. So that's one product, and then the other product will be here. Right. So the actual reaction here, we know that the hydroxyl group has an A value of somewhere around 0.7 kilocalories per mole, right? And so the axial, with the OH being axial, and remember when we talked about the A values, we talked about what that means. It's the difference in energy between the OH being axial versus being equatorial. So the delta G between those two. So you got an A value about 0.7, right? So the oxygen being axial costs more energy, right? And the fact that the oxygen costs more energy to be axial is going to slow down the reactivity, right? Because it's a higher energy substrate, so it's less available, right? So when those two isomers are reacting, the cis and the trans, where the OH is axial versus the OH being equatorial, the equatorial species is going to react faster. So the trans species is going to react faster, right? So this is trans, and then this is cis, right? So the trans is going to be lower in energy, more stable, and then therefore it's going to react faster in this acylation reaction. So that's one example of how the conformation of the ring can actually affect the reactivity. And we look at another example where we take the same trans and cis 4-tert butyl cyclohexanol. We take those two, but we do an oxidation on them with chromium oxide, chromium trioxide. Let's see what happens there. So we would take so this is my trans isomer, and then this is my cis isomer. This is not the chair flip now, because if it was the chair flip, then the tert butyl would also change positions, right? It's just two different isomers, the trans and the cis. All right, but it's not the chair flip, so don't get that confused. Because if it was a chair flip, a conformer, then both groups would change positions, right? The tert butyl group would also change from equatorial to axial in a chair flip. So this is my trans isomer. This is my cis isomer. And if I treat both of them with chromium trioxide as an oxidant to oxidize that that alcohol up to a carbonyl, right? In this case, again, you see the same reactivity. You see the trans isomer being more reactive, right? And let's look at it. So here is the intermediate. I'm just going to draw one and copy it. All right, so it's OCr. I mean, I got to shrink that down just a tad. Sorry about that. All right, so this is the intermediate, and this is where my oxidation takes place. So of course you got an axial hydrogen here that's going to get removed. Right, and that's where your oxidation is going to take place. Right, but again, with the OH being equatorial and you having to do this elimination, right, when you compare that to the cis isomer where your oxygen is, and let me put my Tert butyl back, sorry about that. When you compare it to the cis isomer where your OH is axial, and this is the intermediate chromate that you form, you actually can't do the elimination. Right, you actually cannot do the elimination because the geometry is not properly set for that. So you cannot do. Right, you can't do the elimination in this case. Right, and that's another because you need that proton to be axial so it can be properly deprotonated, and then you can donate into the right orbitals and all that. So for the trans, I'm sorry, for the cis, right, you can't, doesn't eliminate, but for the trans it does. Right, so the trans again is going to be more reactive, and it's going to react faster, just from the perspective of energetically, the trans is more accessible. I'll put that down here. All right, so the trans energetically is more accessible. All right, any questions about any of the two examples that we just looked at? All right, let's look at real quick. We're going to go back and talk about conformational concepts dealing with alkenes, and then we'll be done with this section. The next section, we're going to do is isometric catalysis, because we talked about organometallics already with alkenes, and we talked about ylids, stabilized ylids, and reduction of alkynes. We talked about that with hydrogenation, as well as the hydroboration chemistry. So we're going to, the next topic on Friday, well, not on Friday. On Friday, we're going to do a literature day, because we skipped a couple of those. But on Friday, we'll do another lit day. And I think Sam sent an article, so I want to look through that. And I also have a plug at Penn State. So if I give you an article, you can send it to her and she'll actually find it for you and email it back to you. If we can't access it here, it'll be faster than going through the library. So I'll give you that information. I'll text it separately because I don't want to just, I can't put it in the chat while I'm sharing my screen. And I don't want to just blast it over email, so I can text you the information. All right. So we've already seen.
Also need be.
Go ahead.
Also need be. I have access to Auburn's if we need to use that sometimes too.
Okay. All right. Appreciate it. So we talked in before about the A13 interaction, and let me just recap that. And so we normally see this with an allylic type system like this. And that system, you know, you got two conformations that you can work out of here. So you have here, if it's bisected, where these two groups are overlapping. Right? That's going to cost you some energy. It actually costs about 3.9 kilocalories per mole. Right, for that to be in that bisected conformation. Right, and again, you have conformational mobility, so you can rotate around this carbon-carbon bond right here and get that methyl group away from that interaction, right? So if we do that, then we can rotate around and have this in a different conformation, a lower energy conformation, where you can put the hydrogen inside and then the methyl group here. Right, and I think we showed the example already of this being used for hydroboration oxidation reaction. But I can show it again, there's no problem. I'll just abbreviate the example. So that methyl group here. Methyl group here, and then benzo protected alcohol. All right, so that's this is my substrate, and then if I treat that with BH3 and then follow it up with hydrogen peroxide, right? It's going to give me a hydroboration oxidation product. So I'm just going to copy this right quick. That's the benefit of working virtually. So that's OH, and then now this methyl group here is wedged, and then we'll have another product. Make sure I get all of it. All right, we'll have another product that looks like shrink that down some. Another product here where the methyl group over here is not wedged, it's now dashed. right? And these are, and I'll put a plus here, so that plus that, it's an 8-to-1 ratio, and with this being a favorite product. And again, the way that the stereochemistry in this case is controlled is that, first of all, the hydroboration part, the boron is and the hydride are going to add from the same face, right? So it's going to be one of two transition state conformations that we'll have, and that'll be favored or disfavored. So in the favored conformation, you have right. So this is your, let me just write that as a methyl. This is your favorite conformation, and you can see right away it's the inside A13 interaction that we're concerned about. That's going to either destabilize. That's going to either destabilize or stabilize this substrate, right? So this is hydrogen. This is OBN, right? So this is favored, right? As you can see again, that inside interaction is between a methyl group and a hydrogen. And in this case, boron is coming from the bottom face. Right, and so that gives rise to that the isomer that's present. Let's label them. We'll call that 1 and that 2. So this is gonna give me isomer 1. Right. So the boron is coming from the bottom face, and the conformation that this transition state, in the transition state that it reacts through, is this one, right? Where the hydrogen is inside with the methyl group, and there's very little steric interaction going on, right? The second conformation, the one that's competing in the transition state, that's still methyl on this side. Now you have that methyl group inside. H is here, and then this is with boron coming from the top face. All right, so this is going to be disfavored because of the fact that you have this huge A13 interaction right here. All right, so it's going to disfavor that this transition state and favor the other. So that's really going to be really a hugely destabilizing interaction, and that's really how most of your reactions are going to be governed, especially if it's a competitive process. You're going to have some destabilizing factor in one of your transition states that's going to cause the other transition state to be favored. All right. So as far as the A12 interaction is concerned, let's look at an example of that, and then I think we can wrap up this section and we can move on to another section. So for an example whether A12 interaction is observed. Normally you observe this with 1,1 disubstituted alkenes. So 1,1 disubstituted alkenes. So something like this, right? So that's a example of a 1,1 disubstituted alkene, right? So if we have let me fix that. Sorry about that. Right. So we have an alkene, 1,1 disubstituted. Like this, right? It's the same kind of idea, right? So A12 is similar to the A13, right? You count back to the alkene 1, 0, and then 1, 2. So that's where your interaction is going to take place between the substituent that's at 1 and then the substituent that's at 1 on this side. Sorry about that. And then the substituent that's over here, right? So for that alkene, it actually has two conformations, right? You can have this conformation where you got methyl here, and then the methyl group here. Obviously, you can see right away that there's going to be some steric interaction here between these two groups. Right, and so that is an example of your A12 interaction right there. Right, and the way you alleviate that is the same way you alleviate most steric interactions, right? If you got some free rotation around any bond that's present in there, then you can actually rotate. So you actually have free rotation. It's not really free because you still have some torsional strain, but you got free rotation around this sigma bond right here, right? So you can rotate that sigma bond, you can rotate around that sigma bond and generate a new conformer. Listed here. And I'm cheating, so. But the good thing is the notes are being blackboard. I just know we're running out of time. Right, so you can see here, that's your interaction now. After, let me put my equilibrium arrows in because that doesn't just happen. Right, so those are your two conformers that you can react through, right? And so, again, this is the example, but what about the application? So if we take if we do this directed oxidation with VO-ACAC, I'm gonna show you that. And the reason I say it's directed is because the hydroxyl group here, that's the directing group. That's what's gonna bind to your metal and facilitate the oxidation. And again, this is a 1,1 disubstituted alkene, right? So I'm gonna treat that with vanadium, this vanadium catalyst, VO-ACAC. And the ACAC is just a ligand, acetyl acetonate. and then treat it with Tert butyl hydrogen peroxide, right? And this is an example of a directed epoxidation. Right. So let me show you the products, and then I'll show you the transition states and why one product is favored over the other, and then we'll stop right there. So this is one product. All right, so that's one of my epoxidation products. And the other product is this isomer. All right. So you get these two epoxidation isomers, and they are, the ratio between them is 95:5. All right, so this is my favorite isomer up top. Let me fix that now. All right, so favorite is the isomer where the hydroxyl group and the epoxide are on opposite sides of one another, and then the disfavored is where the hydroxyl group and the epoxide are on the same side, right? And so what's proposed is that there's some interaction in the transition state where that destabilizes one over the other. So let's look at the first transition state proposal. All right, so here is your and this conformer where the OH is here, and it's going to direct the oxidizing agent from the bottom face. Let me hold on 1 second. Let me put the other group in first. I can just write over it. So that's my methyl group there, and then this is the other methyl group that's on that chiral center, right? And you can see again, if you look at the methyl and the hydrogen, that 1-2 potential 1-2 interaction is not there, right? So when the OH is delivering the oxidant from the bottom face of the alkene, this is your favorite transition state. And then by the same token, if we look at the second possible transition state, where the OH is delivering from the top face, because it's a directed epoxidation where the OH kind of grabs onto the vanadium, and then the OH can deliver that oxidizing agent to either face, right? So that's my methyl group back here, and then my hydrogen is here, and my methyl group is here, right? So now we got a problem here, right? Where this methyl group and this methyl group overlapping, they're basically eclipsing one another, kind of like what we saw in the Newman projection. And so this steric interaction is destabilizing. Right, and if I'm not mistaken, the amount is about plus 31 kilocalories per mole, which is a huge amount of energy. Right, that's a huge amount of energy. That's a lot. And so with it being such a destabilizing interaction, that's going to highly disfavor this transition state over transition state 1, right? Transition state 1 will be highly favored over transition state 2. All right. So we're going to stop there. But again, I just wanted to make sure that we touched all these different steric interactions. So we looked at 6-membered rings, and we looked at the anomeric effect. We looked at the A values having substituents axial versus equatorial. And so that last question on the problem set, you should be able to answer that question now. I don't have access to it, or otherwise I'll pull it up, but you should be able to answer that question. And if you need a have a model set, you could build that and see it. But if you don't have a model set, I have here it is right here. Relationships between the substituents, if they are 1, 2, 1, 3, 1, 4, and whether or not they'll be axial or equatorial in the chair. So I'll upload that to Blackboard. That way you'll have it and you can use it to finish out that question, the problem set. I'll also upload a list of A values as well. So, because you're going to need the A values in order to know what's preferred to be axial versus equatorial. So I'll upload all that. I'm doing this now from my iPad because I'm not at home. But when I get a chance to get to my laptop, I'll upload everything you need. You can finish that problem set. And then on Friday, I'm gonna take a look at the article that Sam sent, and then from that, I'll probably send you a couple of articles to discuss. And then I still haven't forgotten Morgan about the vaccine either. So we're gonna talk some about that on Friday too. All right. Anybody got any questions?
Okay, that's fine.
All right. Y'all take care, and we will come back on Friday, God willing.
All right, you have a good one. Stay safe.
All right, y'all. Thank you. Y'all too.
Thank you.
All right.